Good afternoon and good evening to those of you in Europe, and good morning to those of you awake in Australia. Welcome to Session 5 of the ESIG 2021 Fall Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I will provide a few brief opening remarks. As I think you know, we are a global membership-based nonprofit organization providing objective technical information, resources, and networking opportunities in support of grid transformation and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working groups, and task forces for our members, and by producing technical resource material and briefing materials for decision makers. Our workshop sessions are all being held online and are open to everyone. This workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matevosyan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make ESIG what it is, and we encourage you to become involved if you're not already. You can find us on the web at esig.energy, send an email to info@esig.energy to get our monthly newsletter, and follow our activities on LinkedIn, Facebook, YouTube, and Twitter. ESIG also serves a leadership role in the Global Power System Transformation Consortium, often called GPST, whose mission is to bring together key actors from around the world to catalyze a rapid, clean energy transition at unprecedented scope and scale. ESIG leads Pillar 1 of the GPST, which deals with the research agenda for the system operators. More information on GPST can be found at globalpst.org. In the workshop sessions this month, you'll see the range of issues that need our attention today. If you participate in our working groups and task forces, you'll be working with world-class domain experts on issues that need our attention tomorrow and will be on the agendas of our future workshops. As I mentioned a minute ago, ESIG is a membership-based organization, and this is why your membership and your participation in ESIG are so important. If you are the member point of contact for your organization, please keep an eye out for the annual dues invoice later this month. I thank you if your organization is currently a member and strongly encourage you to consider joining if you are not. Regarding logistics for today, I would ask you to note that the session will be an hour and 45 minutes to allow a little more time for presentations and especially for Q&A and discussion at the end. We'll have 4 presentations of 15 or 20 minutes each in the first part of the session, followed by 20 or 25 minutes of discussion and Q&A after the last speaker. As we are doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. You should go to slido.com on your device and enter ESIG21 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also at the bottom of the background slide for the webinar, and you will be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. We will follow up with written answers to any questions we don't get to during the Q&A. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG21 as the event code. We would also ask you, if you're comfortable, to identify yourself when you ask a question so we know who we're talking with. Today's session is all about ERCOT. We were planning to be in person in Austin when we put this agenda together. We even had a visit to the ERCOT Control Center lined up when we got overtaken by the COVID. Recent events notwithstanding, there are a lot of good things happening in ERCOT, and it's well worth a session to take a closer look at it and see what we can learn. It's also worth noting that ERCOT is one of the founding system operators of the GPST. Much of the Pillar 1 research agenda has been built on work in the area of inverter-based resources and grid-forming inverters, an area which ERCOT is leading for ESIG through the high share of inverter-based generation task force in our reliability working group, some of which you will hear about today. Jason MacDowell of GE Energy Consulting, a long-standing member of ESIG, will chair our session today. Jason works with a bright bunch of people focusing on a broad cross-section of activities dealing with the electric system and energy systems integration. Jason chairs the ESIG Reliability Working Group, which I mentioned is where all of our work on IBRs and grid-forming inverters is getting done. Jason is also very active in the standards world through activities in NERC, the IEC, and IEEE. He's been an active participant in ESIG workshops, tutorials, and webinars for many years. He brings a world of experience and a valuable perspective to everything that we do. He's a good friend and colleague, and I'm very happy to have him here today chairing the session. Jason, we appreciate your participation, and I'll now turn it over to you.
Excellent. Thank you, Charlie, for that gracious introduction, and good day, everyone. Welcome to the 5th ESIG session, as Charlie mentioned, in our fall technical workshop that focuses on ERCOT, the Electric Reliability Council of Texas. I'm Jason MacDowell, Senior Technical Director at GE Energy Consulting and Chair of ESIG's Reliability Working Group. It's a pleasure to host you at today's expert panel session. Before I introduce the panelists in a minute, I'd like to kick things off by summarizing kind of where we've been in this seminar and some of the past seminars. In earlier sessions, in some of the earlier ESIG workshops, we've discussed many aspects of grid integration, of variable energy and inverter-based resources. Our world is certainly changing at a record pace with new available technologies, new system challenges, new mechanisms to deploy that technology, and new tools and methods to assess grid stability and interoperability needs. Certainly a pleasure to dedicate this session to one system operator that has experienced some of these challenges early and has established practices and expertise that many other systems around the world are learning from and have learned from in the past. The 4 panelists in our session today are deep experts in their field, and ERCOT's collective experience and expertise around the world regarding grid integration of inverter-based resources, frequency response, grid stability and interoperability of all resources together have really offered many best practices to our industry, and we're very lucky to hear from our panelists today on such subjects. So with that, we'd like to build our panelists, and before we move to the introductions, as Charlie said, we're going to hold a brief Q&A session at the end of our session through Slido. Slido code is ESIG21. And with that, I'd like to introduce our first speaker, Julia Matevosyan. Dr. Matevosyan is a lead planning engineer at the Electric Reliability Council of Texas Resource Adequacy Group, primarily working on adequacy of system inertial response, system flexibility, frequency control, and performance issues related to high penetration levels of inverter-based generation. Dr. Matevosyan is a very active expert participating in ESIG and a leader of our reliability working group and high penetration task force, now drafting a white paper on grid forming technology. It's certainly a pleasure to provide the floor to Julia. Julia, please take it away.
Thank you, Jason. Can you hear me?
Yes, we can hear you well.
All right. Thank you so much for the introductions. Just before we go on to presentations, I wanted to remind everybody or point out to everybody that this session is meant to concentrate on technical issues related to integration of inverter-based resources into ERCOT system, and respectfully asked everybody to refrain from questions related to February event or any ongoing discussions about policy and regulatory changes to ERCOT. So with that, thanks so much. And I'll move on with my presentation. As Charlie mentioned, this fall workshop was supposed to be in Texas again. Last year it was supposed to be in Texas too, and that's why Dan Woodfin was doing excellent keynote opening remarks talking about history of inverter-based resource penetration in ERCOT. So he covered a lot of issues, what brought us up to where we are today. And I just wanted to fill in some things that happened since or in between. So I'm not going to repeat what he was talking about, but rather talk about some of the newer things that maybe happened since. So just to provide some background about ERCOT, ERCOT is independent system operator. We don't own any generation, any wires. We operate ERCOT grid and electricity market. We cover 90% of Texas land, 90% of Texas load, 75% of Texas land. Peak at 75 gigawatts. We are not synchronously interconnected with the rest of the US and have a small number of DC ties of about 1.2 gigawatt altogether. So moving on to some more facts about generation mix. It's about more than 50% gas-based, a fair share of wind generation, some coal, nuclear, and some small amount of solar and storage, but both of those are picking up, and you'll see on the next slide. So this is showing history of inverter-based resource developments from 2012 onwards. In dark blue color, you see installed wind capacity. In lighter blue color, this is planned wind capacity. Dark yellow color is solar capacity. Lighter yellow color is solar capacity that's being planned. And finally, the dark purple color is installed battery capacity, and lighter color is showing what's planned. When I'm saying planned, what I mean is projects with signed interconnection agreements. So the queue actually is larger than that, but we are mainly focusing on projects with signed interconnection agreements. When we're doing studies, then there are even further criteria that we consider to include projects or not. We've reached more than 66% instantaneous inverter-based resource penetration level this March, the past March, when 66% of load was served by wind generation. And why it's just wind, not solar? It's because it happened in the middle of the night. But you can see we are facing pretty rapid solar development, where we'll have about 10 gigawatts by the end of this year, and potentially 10 more gigawatts can be added next year and the year after. So solar is rapidly catching up with wind development. So currently, just to summarize what I showed in the previous chart briefly, we have more than 45 gigawatt of inverter-based resources that are planning to be connected to our system by the end of this year. And potentially by 2023, we can reach almost 75 gigawatts of inverter-based resources on our system, including wind, solar, and battery storage. So as of today, most of wind and solar generation is in the west part of Texas because of better resources and better land availability. And so what it results in is long distance transfer to load centers, which are in the east and central part of Texas. And also in this area, there is limited amount of synchronous generation, and also during times when inverter-based resource output peaks, like in the middle of the night when it's windy, or in the middle of the day when it's a lot of solar and wind as well. Synchronous generation tends to turn offline because it's uneconomic to operate, and so there may be periods of time when there is almost no synchronous generation in this area, resulting in weak grid issues, which you'll hear more about from my colleagues. And similar issues are creeping up in South Texas as well. So there are similar concerns there too. With that, we're seeing increased number of stability-related constraints, which we manage through generic transmission constraints. And Prabhu will talk more about that, and Jameson will talk about one specific study that is being done to see what are the solutions to alleviate West Texas stability constraint that goes through the entire state, right here. All right. So with more inverter-based resources, as I mentioned, there are increasing stability challenges in some areas. This requires us using more different tools and doing different studies. We are now routinely using PSCAD to carry out EMT studies for parts of the grid in Texas Panhandle, near Panhandle area, and also for South Texas. We've been using a weighted short circuit ratio assessment. So this is to calculate short circuit ratio for the entire Panhandle area and evaluate grid strengths using this metric. We're using PSSC to do dynamic studies and VSAT to use for steady state voltage stability studies. This is all in planning. And then in operations, again, we're using weight short circuit ratio tool, online VSAT. We are currently working on online dynamic stability assessment, and Prabhu will be talking more about that. And while we're working on that to determine limits on those generic transmission constraints or stability-related constraints that I just mentioned, we use offline tables that are based on offline studies. And at times, these tables used to be, they can be too conservative and provide too conservative limitations, or at times they may not actually capture actual grid conditions and be maybe they're not too restrictive enough. So it would be better to move on to online dynamic stability assessment. So all of these tools, they lead to need for increased modeling accuracy. We need more tools, and also the tools that we have require more simulation efficiency. And Shawn will be talking more about that, but for example, running EMT studies for even parts of the grid may take a really long time, and so that requires improvement, and there is a gap. We also need more communication with developers and generator owners once the project is commissioned to get models provided to us at first and get them continuously updated if something changes at the plant. So just to again stress out this point, I wanted to talk briefly about Odessa disturbance event. You maybe have seen in the email report that came out from NERC with evaluation of this event. So what happened on May 2021, a single line to ground fault at a combined cycle plant near Odessa, Texas was cleared normally within 3 cycles. The fault caused voltage in the area to drop, but generally it was within voltage ride-through envelope, and voltage recovered very quickly after the event. However, a number of transmission-connected inverter-based resources, primarily solar PV, exhibited reductions in megawatt output, which lasted from a few seconds to several minutes, and that was caused by a fault event. The preliminary review showed that dynamic models provided by resource entities were not able to reflect all of the tripping issues that actually happened, and we need a process for model improvement. So here on the right-hand side in this pie chart, you can see percentages of different types of trips, trip causes that happened, and amount of generation we lost. So this is what was lost in initial event, just clearing the fault, and that was 192 megawatt of combined cycle plant. But cumulative solar plant loss was more than 1 gigawatt. So what this is saying is that we are constantly improving a process of provision of models, model testing, model validation, but there are still some things that are not being caught in this process, and we still need to improve that going forward. So switching gears, we talked previously about inertia monitoring that we have in the control room. So this one is just showing a history of integrating wind generation into ERCOT from 2013 up until this chart covers till March, I believe, of 2021. And also showing inertia distributions in every year. So the minimum is what we're interested in, so the lowest point on the distribution. We set up inertia monitoring in 2013. 2013 started monitoring, in 2015 put it in the control room. You can see that as we added more and more inverter-based resources in our system, inertia actually didn't decline as fast as we expected, and remained almost constant we hit pretty low value at 109 gigawatt seconds this March, but it might have been affected by consequences of February event. So probably it's an outlier, but we'll keep monitoring and trending it next year as well. So all in all, just going to inertia and frequency containment concerns, we thought there may be a concern, so we defined early on what's critical inertia level, which is a minimum level of inertia that will ensure frequency containment reserve has sufficient time to respond, and so we don't touch the first step of under-frequency load shed. We since monitor inertia in real time and forecast it several hours ahead. If inertia gets close to critical inertia level, which is currently at 100 gigawatt seconds, the operator can start additional synchronous generation and bring inertia back up. Above critical inertia, we base reserve requirements for frequency containment, which is called responsive reserve service in ERCOT, based on expected inertia conditions. So at high inertia levels, we need less reserve, and at lower inertia levels, we need more reserve. Faster frequency response is more effective than traditional governor response in lower inertia conditions, and so fast frequency response product has been introduced as a sub-product of our responsive reserve service to ensure faster and earlier response. This allows us reduction of overall reserve amount, and also once this product is fully subscribed, we can actually reduce amount of critical inertia that we need. So this is just showing this introduction of these two new products that I was just talking about. So one was to responsive reserve service, as I mentioned, fast frequency response. This one was implemented in March 2020. However, the process of implementations of this new product into our system still continues, and it will finish in December this year. So partially, there is capability for some resources to participate in FFR already, but after in December this year and after that, this product will be fully implemented and resources can participate. And so this product is quarter of a second response time to frequency trigger of 59.85 hertz. And these two products were already existing in our responsive reserve service. So this is traditional governor or governor-like response. And then we also had a fast frequency response product provided by load resources with under frequency relays. And so this is half a second type of response, step response to a frequency trigger of 59.7 hertz. And this was another product that got introduced to our ancillary services, which is 10-minute ramping product, and this will be implemented at the later stage. So I just have it on the slide here, but I didn't really mean to talk about it much. So switching gears to battery storage, we are seeing rapid uptake in interest in battery storage development. So by the end of this year, we'll have more than or close to 1.5 gigawatts of storage. And then you can see that queue is rapidly growing in the next 2 years. What prompts this interest is declining technology costs. There are federal incentives for co-location of batteries with PV projects. There are price spikes during scarcity hours, which incentivize participation in energy arbitrage, and then large-scale energy storage in utility-scale energy storage in ERCOT can participate in energy markets and ancillary services markets. And it's actually, I don't have it mentioned on this slide, but we also have a project in works where distribution connected storage resources, which are larger than 1 megawatt and register with ERCOT, can participate as a resource in our energy markets and ancillary services markets, and that includes storage as well. So this project will be fully rolled out probably by January 2022. So as we have seen this pickup in interest for storage, we had to think about how to integrate it into our systems. We didn't have models for storage in our network modeling system, energy management system, market management system, and settlements. So we had to think how storage should be represented. So we first went with what we had available, and we used generation resource model and so controllable load resource model to represent storage. And controllable load resource, it just means a load resource that can continuously control its consumption. So it's not step type of resource, but controllable megawatt consumption. And so what initially happened, we represented storage as two separate resources, and that's cumbersome because sometimes they can get conflicting dispatch instructions because our systems didn't see them as part of one resource. So the first step we did is linking those two in our system. So now they don't get conflicting dispatch instructions. But this is still kind of cumbersome because these are not two resources. This is actually one resource, from negative to positive output. And so the next step we are working on right now is to implement single resource registration into our registration system. So when the developer comes to ERCOT and wants to register, they have to kind of fill in all the information as if it's just one resource. And then on our side, it's still modeled as two separate resources, as I previously mentioned. And then what ultimately would like to get to is just model it as a single resource all throughout, from registration to operations.
Julia, we've got 5 minutes left. Thank you.
All right, great. Yeah, I'll have plenty of time. So we're also seeing uptake in hybrids or co-located resources. As I previously mentioned, one of the drivers is a federal incentive for co-locating with solar. And this is where we're seeing most of the interest. So this pie chart is showing overall battery resources in ERCOT. And this is the interconnection queue of projects that started full interconnection studies. So you can see this number is much higher than what I've shown in previous charts, because previous charts were showing projects with signed interconnection agreements, whereas this is a bigger set of projects and includes projects that started full interconnection studies. So 65% of those projects looked like they are standalone, and then 29% are co-located with solar, 5% are co-located with thermal capacity actually, and 1% co-located with wind. And just to mention, with co-location with thermal capacity, I think the interest there is to enhance participation in ancillary services for gas turbines, where they can use battery to provide initial response and then use gas turbine to provide sustained response in frequency responsive products, for example. We're seeing mainly projects that are AC coupled, so they're not using same inverter to connect the battery and solar resource, but a few projects that are DC coupled. All right, so in summary, ERCOT has successfully integrated nearly 45 gigawatts of inverter-based resources so far. There is significant amount still projected in the near future. We're seeing an increasing number of stability-related transmission constraints, which you hear a lot more from my colleagues. And this is due to high inverter-based resource concentration in certain areas remote from load centers and from rest of synchronous generation. There is increasing complexity in simulation tools and models and model validation processes, increasing need for real-time simulation tools. Inertia and frequency containment has not been an immediate concern, and currently is being addressed through increased situational awareness and introduction of new ancillary services. There is increased interest in battery storage and also hybrid resources, and that requires a number of changes to ERCOT systems. And I just wanted to point out that this is not just down to figuring out how to do it. It actually takes much longer time to make those changes to the systems, and at times can be prohibitively expensive to make certain changes, and takes a long time. So with rapidly growing interconnection queue, we still have a lot of work ahead of us, and I'll let my colleagues talk about some of the initiatives. Thank you, Jason. Thank you, everybody.
Excellent. Thank you, Julia, for that excellent presentation. And looking at Slido, we already have some great questions that have come through. So just to remind everyone, Slido code ESIG, ESIG 21. And please don't forget to vote up your favorite questions. So next, without further ado, I'd like to introduce our next presenter, Shawn Wang. Shawn is a senior planning engineer with the transmission planning department at ERCOT. His expertise has been focused on the modeling and control of power electronic devices in power systems. His current role mainly involves dynamic analysis of inverter-based resources and large-scale EMT simulations in ERCOT. And it's certainly a pleasure to have Shawn speaking with us today. Shawn, please take it away.
Can you hear me okay?
Perfect. Thank you, Shawn. I can hear you.
Okay, thank you. Yeah, thank you, Jason, for the introduction. Yeah. Hello, everyone. My name is Shawn Wang from ERCOT. Thanks, Charlie, for the invitation, for this opportunity to present the PSCAD study experience at ERCOT and exchange some experience to the audience. Let's start. Yeah, the outline of my presentation is listed in this slide. Yeah, first of all, I will introduce some background in the Panhandle area. Then I will focus on the 2020 Panhandle stability studies using the EMP studies. And also mention the PSCAD model quality test requirement at ERCOT. Yeah, some of them relate to the point raised by Julia in the previous presentation. Also, I'll mention the Pikachu developed at ERCOT for the large-scale the PSCAD studies. Also, I will present some sample model quality test result for your reference. And lastly, I will mention some next steps. Let's start. Yeah, I think in Julia's presentation, he mentioned the high IBR penetration levels in the ERCOT system. Actually, in my presentation, I mostly focus on the Panhandle and nearby Panhandle area, which is located in the northwest part of the ERCOT system. Actually, this system, this area is remotely located at the ERCOT ERCOT boundaries and the far away from the load centers like Dallas, Houston area. Actually, in this area, the generation capacity can be like gigawatts, multiple gigawatts generations, which will export it to the load centers far away through the long transmission passes. In this area, the generation is all inverter-based resources, actually, all IBRs. Actually, this trend, actually, in the last decade, there's a huge amount of IBR resources developed in this area, and this trend is still keep growing. Actually, in this chart, we can see in the last decade, actually, in both Panhandle and nearby Panhandle, the IBR capacity increased quite a lot. Toward the next year, only in this area, probably the IBR capacity can be more than 11 gigawatts. Actually, one thing I want to highlight is that on this tilt part, actually reflect the fact that there are solar generation popping up in this area in the near future. Actually, with all these factors taken into consideration, actually there are some operational challenges, actually such as the voltage stability and the control stabilities. As mentioned in Julia's slide, actually for the voltage stability, actually we can capture those by using the positive sequence models like PSSC or the TSAT models. But for the control stabilities, we need to use the EMT model or the simulation tools to assess the control stabilities in these areas with high penetration of IBR resources. Actually, at ERCOT, since 2016, we started develop the system-wide EMP studies. Through those studies, actually, we identified 2 synchronous condensers needed. And these 2 condensers are installed in the 2017 time frame, actually in the Panhandle area, to enhance the system strength and provide the dynamic voltage support. As I mentioned, the EMT study, basically the PSCAT study in ERCOT, start from 2016. Actually, this chart shows the development, the case expansion since 2016 up to last year, 2020. Actually, from this chart, we can see the IBR capacity keep growing from study to study, and even for the physical boundary, actually moved further and further to the ERCOT system. Actually, one more thing I want to highlight is that in this PSCAT study, actually we use the parallel setups, actually use the multiple CPU threads to handle the large scale PSCAT cases. From here, we can see from the beginning, actually we used 16 CPU threads, but in the last study, the CPU threads can go up to 43, which can be see details in the next slide. Yeah, in the last PSCAT study, actually we include a total of 46 IBR projects, and represented by the 62 PSCAT models. We distributed those single PSCAT case to 43 threads, use the 43 threads to simulate each PSCAT simulation run. In each PSCAT run, actually we distribute those IBR projects to the 42 slave cases, which connect to the main case through the TCP/IP communication protocol. Actually, in the master case, actually include the panhandle network, actually include around 500 buses. We also include the synchronous condensers, two synchronous condensers, and the SVCs in the master case. The rest of ERCOT system actually was represented by the multiple port equivalent network, which also include in the master case CPU thread. Some highlight or takeaways from this PSCAT study is listed in this box. First of all, actually, we take a lot of efforts to prepare the base case, even we leverage the experience from the previous studies conducted by electronics. We still take quite a lot of efforts to prepare the base case. For each contingencies, actually it took like 2.5 hours to finish one run and create 3.2 gigabytes data for processing. Actually, in this study, we run 36 contingencies. You can imagine how much time it took to finish all the studies. Another point I want to mention is we took a lot of time for the individual model update and the quality improvement for the PSCAT models in this study, which will be talk about more in the future slides. This slide just show the comparison result between the PSSC and the PSCAT result in terms of the total power generation in the panhandle and the nearby panhandle area. From this plot, we can see that there's some mismatch due to the model tripping in the PSSC and the PSCAT models, and some model difference in the individual models. Other than that, actually they match to each other, actually match closely to each other, and shows that the system is stable in these environmental conditions for the investigated disturbance. Yeah, as I mentioned, actually we took a lot of time for the PSCAT model quality improvement in this study. In general, actually the PSCAT model are expected to better reflect the IBR performance and weak grid conditions. But we realize that the PSCAT model quality and the accuracy still need to be validated and verified for at least two purposes. First one is to improve the fidelity of the system level study, and also to be used as the reference to benchmark the positive sequence models like PSSE and TSAT. From our experience, we realize that the model review and update process often require the support from the resource entity, the developer, manufacturers, the consultants, or even the TSPs, which can be very tedious and time consuming, which is another factor to contribute the system level PSCAD study to be much more time consuming. To this end, actually, we address those issues actually in the recent, or actually the March of this year, we put additional language to the PSCAD model quality test, model quality improvement requirement in the ERCOT planning guide. Actually, this chart, flow chart, shows the model requirement on each stage. Start from the left-hand side. Actually, by beginning to start the generation interconnection process, we request the PSSE model and the model quality test at this stage, at the beginning. Actually, in this stage, if the SSR study risk is identified, then we will request the PSCAD model and the model quality test report, which is detailed in this column. Yeah. Otherwise, actually, the PSCAD model will be requested to be get the project into the QSA process, which stands for the quality stability analysis. For this part, actually, our next speaker probably will talk about more on this topic. But here we only focus on the PSCAD model part. In this stage, actually, the PSCAD model and the quality test report need to be provided. Also, the PSCAD model unit model validation report also need to be provided. In this requirement, actually, this report is benchmark the PSCAD model result against the lab test, actually, such that we can make sure the PSCAD model, the accuracy to reflect the actual devices. To be noted that in this requirement, actually, we don't require this test is not project specific. Rather, it's only technology specific. That means actually for the same technology, you can provide the same report for different projects. Another one is like in this stage, actually the benchmark between the PSSE and the PSCAD models need to from the performance wise, they need to benchmark to each other based upon the model quality test reports. When the project moves to the commissioning stage, the developer need to provide the parameter verification actually for the key settings for the PSCAD models, such that the PSCAD model, the parameters in these models need to be consistent to match with the device setting in the field. During this stage, for whatever model change or the setting changes, the model quality test need to be redone and the report need to be resubmitted. After the commissioning, the project moved to the operation stage. The model need to be the dynamic models, including PSSE and PSCAD, need to be keep update per the NERC requirement. For the existing IBR projects, actually the verification process need to be done within 2 years of this language into place. And after that, actually every other 10 years, they need to verify the verification process if there's no changes, no setting changes. Last plate is that for whatever, whenever the model change or setting changes during the operation, the model quality test need to be redone and the report need to resubmitted. Yeah. So here we list some links for the details of this language. You can click the link for the slides later on. You can if you are interested. Yeah. Next we talk about the PCAD tool for the PSCAD studies. The PCAD tool stands for the PSCAD Auto Run tool. We developed at ERCOT for to manage the PSCAD studies. for both model quality test and the large-scale system-wide PSCAD studies. This tool is based is a Python-based tool. We leverage the automation library in PSCAD, which makes flexible to update or expand the functionalities. In this tool set actually include the functionalities for the PSCAD model quality tests, which will be described further in the next slide. In this tool, actually we can automatically create and consolidate the simulation plots, including both PSSE and PSCAD plots into one single platform, such that we can conveniently compare the performance result for both models. Actually, for this tool also support multiple runs and parallel computations, which reduce the user manual interrupting for the PSCAD simulation process and reduce the case building time and let the engineer focus on the studies and the result analysis. This diagram shows the PCAD tool for the PSCAD model test. Here, at this point, we include the following functions, like voltage step up, voltage step down, the LVRT, HVRT, and the short circuit ratio tests. For the specifically for the PSCAD models, we also include the phase angle step up, step down tests. Also include the impedance scanning tool, which can be used to scan the IBR models, the PSCAD models, to generate the impedance profiles in both subsynchronous and supersynchronous frequency range.
Shawn, we have about 5 minutes left. Thanks.
Okay, thanks. Yeah, this tool is publicly available in this link. If you are interested, you can download and play with it. Yeah, this chart, this slide just shows some issues identified in the PSCAD model quality test in the panhandle studies. From here, we can see that for this model, actually they have the different performance for different PSCAD version and even for the different Fortune compiler versions. To be noted that in the current study at ERCOT, we are using the PSCAD version 4.63 and the Intel Virtual Fortune version 12, which works well for the other models. Actually, for this site, actually they have some suspicious tripping issue. Actually, by knowing this, actually we can make a better judgment in the system-wide simulation. It is a model issue rather than the system-wide issue. Actually, for the last one is like in some model, actually they have the incorrect rated capacity setting in the model. Seems like it's very obvious to avoid, but it still happens in the reality. We need to pay attention for that. In the next 3 slides, I will show some testing the quality test, the model quality test result in the panel study, in the latest panel studies. For this site, when we apply the LVRT profiles to both PSSE and PSCAD the models, seems like the model in both PSSE and PSCAD shows the acceptable result or reasonable result in terms of both P and Q, such that we deem this model is acceptable for both PSSE and PSCAD. But in this example, we applied the LVRT profiles, seems like the PSCAD model provided the reasonable response, but the PSSE result gives some suspicious response, such that we need to get back to the RE to update their PSSE models. In the last one, actually, when we apply the LVRT profiles, the PSSE result seems like reasonable, but the PSCAD model gives the wrong dynamic VAR response during this VRT period, such that we need to reach out to the RE to update their PSCAD model. Some ongoing and the next steps. Yeah, the PCAR tool has been successfully applied to the ERCOT PSCAD studies, including the PSCAD model quality tests and the parallel simulations. The tool has been shared with the stakeholders to facilitate the PSCAD model quality tests. Looking forward, with the increasing penetration level IBRs in the system, the large-scale EMT studies are becoming more necessary than ever, but we still facing some challenges, like the simulation efficiency and the complexity. But this issue is not only for ERCOT, but also for the whole industry. We need to identify ways to improve the EMT simulation efficiency and explore ways to develop adequate screening approaches to evaluate the system strength and determine when and where the EMT studies are needed. Yeah, lastly, I just show some links for the previous panel studies. With that, I will stop here. Yeah, thank you.
Excellent. Thank you, Shawn. Really appreciate your great presentation. And again, a lot of great questions coming in on Slido. ESIG21 is the Slido code, and keep them coming. And also be great to vote up your favorite questions. I'd like to introduce our next speaker, Prabhu Gnanam. Prabhu is currently the operations department, is the manager of the operations department responsible for operations engineering, shift engineering, and operations stability analysis. Prior to joining ERCOT, Mr. Gnanam held various positions at American Transmission Company in Wisconsin, Simi International, T&D in Canada, PowerTech Labs, BC Hydro in Canada, and is a registered professional engineer in Wisconsin. It's a pleasure to have Gnanam with us today. Gnanam, please take it away.
Jason, please confirm that you can hear me okay?
Yes, can hear you fine.
Perfect.
Thank you.
Thank you. Hi, good afternoon, everyone. Good evening and good morning. My name is Prabhu Gnanam. I'm with the operations department at ERCOT. Today, the discussion topic is I want to share some of the practices and challenges to manage some of the transmission constraints you all heard from Shawn and Julia. So with that, I'll just slide here. Again, this is a background on the inverter-based resources connected to ERCOT. Julia talked about as similar discussions here. We have integrated more than 45 gigawatts of IBR resources. One thing I'll point is between what we have projected for 2021 and 2023, there's a significant increase. You're looking around like 25 gigawatts. This is planned. So we're expecting a lot more of integrating a lot more of the resources in the next couple of years. That has been the trend for the last few years. The key here is most of the resources are on the western side of the grid. So the load centers are basically on the east and northeast of Texas. So we are trying to transport or export this power using long transmission lines, and that causes a lot of issues, especially related to stability issues. So we have similar issues in southern part of Texas. There are issues in the west and far west areas too. So primarily what I'm going to talk about today is the generic transmission constraints. We call them GTCs. These are stability limitations, stability limits we try to manage within the system. I'm not going to focus on the steady state voltage and thermal issues, which typically we manage through the RTCA and SCAD, which is pretty much standard practice across the industry. So the generic transmission constraints, these are they're called different names in different parts of the country and system. Familiar, some of the terms or people use like flow gates. So basically, these are stability limits we try to manage using the current market tools. Put stability limits, translate them into interface limits, and we try to maintain the system reliability. Again, there are a couple of charts in here. One is here we show the trend of the GTCs within ERCOT. So you can see it has steadily increased. In one sense, it's getting to a point where it's hard to manage now. We moved from 4 to 15 over a period of 7 years now. You can see some trend in the middle where it dropped. That is due to transmission improvements that was put in place, but since then the generation additions have pushed more GTCs into the system. So the other map here shows the location of the GTCs. As you can see, we have primarily a big area in the west where most of the renewable resources are. We have several GTCs, and also, as I mentioned, in the south part of Texas, additional resources, inverter-based resources. We see some significant GTCs, and there are some additional GTCs, which has been in the load centers, more of a steady state voltage stability. So GTCs, again, the definitions, as I said, this is a non-thermal system operating limit. We are trying to manage using the current market tools. There is also the term GTL, which is actually the generic transmission limit, which is the SOL for which the constraint is managed. And the next 3 bullets are mainly discussing our guiding principles, how we define this GTCs. Meaning the GTCs should be reliable, efficient, non-discriminatory, and able to manage those ERCOT, manage those constraints to ERCOT operating conditions in current market mechanisms. And again, the generators that form are part of the GTC should have a similar impact on the stability issue that we're trying to manage. So here's a slide which gives a high-level overview of our GTC process. Basically, there are 3 areas I highlighted where we have a planning horizon, operations planning, and the real-time operations. So let me start with planning. Of course, like any other entity, we have like the interconnecting entities trying to go through our ERCOT interconnection process, which is managed by the resource integration group. So as part of that, every individual generator that has to go through the interconnection study process, which includes the full interconnection studies. In case of ERCOT, the full interconnection studies are performed by the TSPs, transmission service providers, and ERCOT coordinates those studies with the TSPs and the IEs. So it's ultimately ERCOT which approves those FIS studies. So once the study is complete, ERCOT will review those. So there are different parts of the FIS studies. Most of you are familiar with. The part we are most interested in is the stability part of the FIS study. There is a stability FIS report which comes out that feeds back into the quarterly stability assessment. So quarterly stability assessment is a fairly new study. It came in 2016, 2017 timeframe. Prior to that, we didn't have a process. So prior to that, it was all managed through the full interconnection study, and then we will try to identify stability issues and try to use the GTCs to manage those. Primary need for the quarterly stability study was driven by the fact that we were managing a lot of interconnections in a fairly short time. So the other part is the interconnection studies. They generally tend to focus on their own stability studies, and also everybody familiar with the process. These studies are done at some different time frames. So the quarterly stability study is more of like trying to do a cluster study, looking at a specific window in the near term. So before this unit's connected to the system. So we do this quarterly study. I'll talk about in the next few slides, give you more details. So then once the quarterly stability study is done, it'll look at a set of generators that's trying to connect in a time frame 5 to 7 months based on the initial synchronization date. So once we do that study, that forms as the input for our GTC assessment. So in the stability assessment, we will identify any stability issues related to the set of generators we study, and then the individual GTC assessment will focus more on a specific GTC for a specific area. Let's say for West, we identify some problems in the existing West area, we will do a GTC study for the West. And if you find something in, for example, in the South, the Valley area, we will do another study and update those GTCs. It could be existing GTCs, or it could be new issues we identified through quarterly stability studies. We will try to accommodate those through the GTC implementation process, which is again the process. Once the GTC is identified, GTC assessment is completed, it will provide the the interfaces to control, the limits. So all these things has to be translated to operator tools and put in place. So that's what the GTC implementation is. And basically changing the network model, creating situational awareness tools and operator trainings, procedures, all those things. Then we manage those GTCs in real time. One of the tools we use is VSAT. That's a separate tool, but the GTCs and the GTLs, generic transmission limits, are based on a static table, which comes out of this process. One of the things I want to point out is the outage coordination. Anytime we have planned outages, we have to update those static limits, because the static limits are only performed for what we call it like base case N-1 and some prior outages N-1-1. So here's additional details on the quarterly stability study. Again, we perform a study every 3 months. This is looking at a specific window. We might want to call it as a cluster study. So the intent of the quarterly stability study is to look at the whole ERCOT region rather than the FIS is more focused on specific window. And also when the FIS study is done, it tries to model the competing generators, but those things change. So in a nutshell, the QSA is to incorporate the latest transmission changes, generation changes, and basically it bridges the gap between the FIS study and the GTC implementation. So what comes out of the QSA is the GTC assessment. As I said, for every stability issue identified in the QSA, we will do a GTC assessment. And this is the process we use to put those GTCs in place. There are some factors pointed here. One of the things is highly dependent on the initial synchronization date of the resource that is driving the need for the GTC. That changes, obviously, the timelines for the GTC will change. Again, in some parts, it might be straightforward where we can use the QSA results as input for the GTC. So here are some of the steps involved when it comes to GTC implementation. I highlighted some of the things we have to consider change. This is getting complex to manage a process which involves so many parts. Basically, you need to change the network operation model, the tools we need for operators, the PI displays, any ad hoc operator tools. Again, as I said, the GTLs are tables. We need to update those multiple tables. And depending, there are some system condition-based tables we need to put in place. And some places we might have to update the VSAT, which is the voltage stability assessment, which can be used as a proxy. In addition to that, of course, we need to update the operators, trainings and procedures, and we have to also coordinate with the market tools and impact we have, especially getting the GTC modeled in a timely manner for the congestion revenue right CRR auctions, and also considerations for GTC in the day ahead. So here's an example of the situational awareness tool, which is the GTC management tool, which shows the displays for one particular GTC. You can see 3 values, basically what's the loading on the existing interface or lines, and you look at megawatt flows, and the last one tells you, what the limit is. So we have certain alarms and customization where you can see if the loading gets about 95%, depending on what the threshold is, you will see those things will be highlighted in the display. So the last process of the GTC this is more of a planning process for every GTC. There is a requirement in ERCOT protocol says that we have to do an exit alternate study or exit strategy for a GTC. So basically, this is done by our planning department. So any new GTCs, we need to perform a GTC exit alternative study within 180 days of implementing the GTC. For existing ones, we have to periodically review those every 3 years. So what this involves is basically we work with the transmission service provider to find exit alternatives. The alternatives could be anywhere from modifying existing gas or putting or recommending transmission, not recommending, identifying transmission. Reason I say not recommending is because these are projects that has to still meet the ERCOT reliability and economic criteria. So once we identify this project, if they meet the reliability or economic criteria, these projects will move forward. You heard some discussions from Julia and others mention about real-time tools. As I said, the GTC, the complexity and the number of GTCs is driving us to look towards more automating this or using a real-time tool to manage this. Basically, what this is we are looking at a tool which is the DSA tools, Transient Stability Security Assessment Tool, TSAT, for real-time operation, for real-time calculation of the GTLs. As Julia mentioned, the current processes use offline studies that's based on certain snapshot conditions or system conditions, and it's designed in a way we need to set those limits conservatively so that we can apply for all system conditions. So once we, this is something we are working on. Probably slide. So some of the challenges, I saw a couple of questions already pop up asking about what kind of models we use for TSAT. So one of the challenges within ERCOT is, as we said, we are experiencing similar certain issues, especially in the regions where we have low system survey. So in those areas, our planning process, we have always used a detailed model. You want to call them user-defined models in PSSC. I know in some parts of our country and other areas, people have moved towards more a generic model. But we, based on our experience, we still need those detailed models to represent some of the issues we're experiencing in the low stress systems in areas. So for us, it's not an option to replace, we can't replace those user-defined models with the generic model. So that was the limitation in TSAT, because obviously over the years, all those generic models were developed for PSSC. So here's a chart which shows where we are in terms of the TSAT model. Obviously, this only represents the user-defined models for inverter-based resources. So roughly, we have like 48.3 gigawatts of inverter-based models, and we have models for roughly 2/3 of the system now. In 2019, we started a market rule change, and we are working with stakeholders, various stakeholders, the resource entities, OEMs, and Power Tech, and other several consultants who are helping the industry to get those models. So basically what we have is, we've been developing this model. So ERCOT system, it's the IBRs are using mostly user-defined models. So one good thing is the TSAT, these models are added, and as you can see, the recent versions, you would see a lot more user-defined models. TSAT is a version, so.
Great. 5 minutes left, Prabhu. Okay. It looks like you're wrapping up. Thank you.
Yeah. Let me see if I missed anything there. So, in summary, I will leave some, comments and thoughts for the discussions. So, the biggest challenge for the GTC process in general, the timelines associated with the generator. So here's some information or data based on what we have seen in the last few years. The trend. Typically, what we see is it takes like 18 to 24 months for IBRs to connect to the system from the initial planning phase to the actual physical interconnection, initial synchronization. So what we have seen is this is broken down for both the wind and solar, the blue is the wind and the solar one. So you could see, the trend is just like, we are like we're getting shorter and shorter interconnection times, especially when you're talking about the planning model availability and the commercial operations data. You can see here, the takeaway is like we are seeing a narrowing of the window where we have decent models to run this study. So really it's only 8 months period where we have like the visibility and the actual models where we can run all the studies, whether it's like a USA study or any other studies done in planning to put some run some PSCAD studies and do those validations. The other one is also, Julia talked about this, we have energy resources, generated resources increases within the system. So we are already looking to see how we can accommodate those. So obviously I'll leave with a couple of comments. And one is the real-time tools, as I mentioned, once we implement this, we would have some, it'll address some challenges, including our outage coordination, which is a huge issue because we have multiple outages. We have to constantly update those GDCs. The last one is once we have a capability to run this real-time assessment, whether it's using the TSAT, we could leverage our PMU measurements or event analysis and do comparisons and do model validations. So I believe that's my last slide. Okay, one more slide. I'm sorry. We have I provided some additional resources. We had a series of workshops last year or so. There's a lot of good materials, especially with the ERCOT process related GTCs, any transmission issues, and we also have a white paper which talks about our practices related to GTC. Last slide. Thank you, Jason.
Excellent. Thank you, Prabhu. Great presentation, and many more questions have come in about the presentation. So we'll get to them in a minute. But certainly, last but not least, I'd like to introduce our fourth speaker, Jameson Haesler. Jameson is a senior planning engineer at the Electric Reliability Council of Texas. He is he's in the Economic Analysis and Long-Term Studies group within the Transmission Planning Department, and his areas of focus include production cost modeling and integrated transmission planning, combining reliability and economic analyses. So, Jameson, it's a pleasure to have you with us today. Please take it away.
All right, thanks, Jason. My name is Jameson Haesler with ERCOT Transmission Planning, and today I'm going to talk about a special study that we at ERCOT are doing that's focusing on the West Texas export constraint, and specifically some of the long-term challenges associated with that, and what we think some of the improvement options might be to address those challenges. And really today I'm going to focus on two areas. The first being the background and really what motivated us to take a look at this in more detail. So I'll talk about larger ERCOT system trends, as well as some assumptions and inputs that went into our study cases. And then the second area I'm really going to focus on are our key results from our long-term 2030 study case, both base case findings as well as performance results of some of the tested improvement options. And really it all starts with the larger ERCOT system trends that the earlier presenters touched on. And here, if we take a look at the different maps first, we can see both load and generation trends. And if we take a look first at the load, the load trend is really a continuation of previous trends in certain regards. There are outliers, of course, but the continuation is that in the large metro areas of Dallas, Houston, San Antonio, and Austin, you're seeing continued large load increase. And then the trends really start to diverge when you take a look at what's happening on the generation side, which has been well covered by the earlier presenters. But if you take a look at this middle map, it shows where a lot of the backbone of the fleet is in terms of thermal units, but they're aging, and you can see a pretty close correlation with those large metro load centers of Dallas, Houston, Austin, and San Antonio. And the new trend is of course a lot of renewable generation, except it's coming on, in the far west area of ERCOT. And these trends together really lead to two main problems that have to be looked at together, which is, first, the stability constraint that results from the transfer, but also the thermal constraints at the load pockets. So they really need to both be looked at together. So zooming in a little bit to the West Texas export constraint specifically, first, what that is as touched on earlier, it's a stability constraint made up of an interface consisting of 16 west-east, east-west, 345 kV double circuits. And we measure the flow across all of those lines. And as the generation trends from the previous slide have started to manifest, we see that result as we monitor flow across the West Texas interface. So this only goes up to the end of 2020, but 2021, the trends continue, and we see a steady but consistent increase of flow across that interface. So, all of that is really what motivated ERCOT to start this study at the end of last year, with the goal of developing a roadmap of transmission improvements that will allow for increased transfer, from West Texas, where all the new units are energizing, to the ERCOT load centers on the eastern side of the state. And what really makes this study interesting is that at least from an ERCOT perspective, it's a first of its kind study where we are combining both dynamics and economics to tackle those two primary challenges that I mentioned, both of the stability constraint as well as the thermal constraints at the load centers. So here, with the larger system trends, as a backdrop, we can take a look at our study cases and some of the primary inputs and assumptions that we made. So we have two study years, 2023 and 2030, and the maps are IBR capacity by weather zone, but really what's most striking is if you just look at total IBR capacity between the 2 years, where going from 2023 to 2030, there's a 75% increase, nearly a doubling of IBR capacity, which is a big driver of why we're looking at this. And then the load numbers here really represent, at least in the reliability cases, a lower load, higher transfer scenario. So these aren't, these shouldn't be confused as summer peak numbers, but to further, make a further distinction within the economic cases, those are running 8760 hourly simulations. So we have 8760 hourly load profiles running in the economic cases. So, if we start taking a look at our 2030 key findings, and we start with the base case from a reliability perspective, we see some problems that we would expect associated with the high transfer, and specifically problems with high megavar losses across the interface, which is not surprising given how your reactive needs are going to increase non-linearly, relative to your active power transfer, and just the magnitude of that transfer across the West Texas interface leads to that. So teal here is our pre-contingency, and then gray here is under the loss of a 345 kV double circuit. And we see the same challenge with angle separation, starting in pre-contingency, already slightly discomforting 30 degrees to a much more discomforting angle separation of 45 degrees post-contingency. And really what these two conditions illustrate are, this is going to lead to dynamic instability prior to reaching any sort of thermal overload. But there are thermal considerations that have to be taken into account. So if we switch over to the economic perspective, staying in the base case, the first thing to note is just how much of the system curtailment is behind that West Texas interface. 88% of all of our system IBR curtailment is behind that interface. And as pointed out earlier with the large metro load centers of Dallas, Houston, San Antonio, that's where we see significant congestion. We see it in all three of those areas. So again, it's the challenge of the dynamic challenges, and then shortly after that, the challenge of the thermal challenges of getting them to the load center. So these were both certainly kept in mind as we transitioned over to testing different improvement options, which at times could be challenging because the best stability solution may not necessarily be the best thermal issue, because each challenge has its own its own preferred solution. So finding an overlap between the two to solve both was the challenge. But after taking all of that into consideration, we focused on three options, which I'll go over here shortly, two of which are AC only, and then we looked at an HVDC plus AC hybrid option when we were testing 2030 solutions. So here's an overview of those three options. So I guess a couple of notes first. So wherever AC is referenced, a low impedance 345 kV double circuit is assumed, and then for HVDC references, a 1.5 gigawatt VSC HVDC line is being used. And you'll see that all three options do significantly increase the transfer capability across West Texas. And then, just as a point of reference, we're talking about anywhere from about 1,000 miles of double circuit lines, anywhere ranging up to 1,300 miles of double circuit lines. So, diving into the results a little bit, but not getting too deep in the weeds here. These two graphs here are flow duration curves of the West Texas export interface on the left and what we call the north to Houston interface on the right, which is basically a primary import path from the north into Houston. And what these curves show, it's basically telling us what percentage of the year is the interface binding at its limit. And then our base case being yellow here, and then how the options, the tested improvement options, perform relative to that base case. So the first thing to note is that all three options do improve the West Texas export capability and lessen the percent of the year that interface is binding. If we switch over to north to Houston, the results are a little more mixed. So again, our base case in yellow here shows what percentage of the year that interface is binding, and then the three tested options show the performance relative to it, where our AC only options actually cause north to Houston to bind at a higher rate than base case, whereas our HVDC plus AC option improves and relieves binding on that north to Houston. And just to touch on that a bit more, so both AC options here, 1 and 3, increased congestion coming into Houston. And when you look at the map, it's a little clear why that is because there's this large transfer from the west, but it stops it stops in the DFW area and isn't able to make its way down to the Houston load center because of that interface limit, whereas option 2 is in a sense going straight to the load and able to bypass that northern Houston constraint. So, while all 3 options do improve West Texas export capability, only option 2, which included that HVDC line, also improved north to Houston. But I think what's even more significant here is that, at least based on our preliminary 2030 results, the West Texas export, even with the dramatic system improvement options studied, it's still expected to be a significant constraint. And again here we're summarizing a little bit some of the performance metrics of these 3 options. But the second point is that the improvement of that West Texas transfer capability is going to potentially be limited by the accompanying thermal constraints, whether it's inside or outside West Texas at the load center. And I think a good representation of that happening is if we look at the first 2 rows of the table here, where our top row is showing our West Texas transfer capability, and you see a rise, an increase going from option 1 to 2, and then again going from option 2 to 3. And typically, as that West Texas transfer limit increases, your economic production cost savings will also increase, simply because you're unlocking the cheaper renewable generation, displacing more expensive conventional generation. So you should see the production cost savings rise. However, if you look more closely at option 2 versus option 3, you do see an increase in that West Texas transfer capability in option 3, but you do not see the same production cost savings that are seen in option 2, which again has that HVDC line going straight into Houston. So really these results just underscore the necessity to look at this, when looking at the interface, also keeping in mind the influence of those downstream as well as upstream thermal constraints.
Jameson, we have about 5 minutes left.
Okay, great. And then here, these just kind of summarize the impact of the options on those large metro areas. They have pretty much uniform performance, except as pointed out a slide or 2 earlier, the difference in how the Houston import is affected by the options. So, with that, I appreciate your time, and we'll transition over to questions here, I assume. Thank you all.
Excellent. Thank you, Jameson. That was a great presentation, and it really rounds out a lot of the subjects we heard about earlier that are focused a lot on stability constraint. Julia and Shawn and Prabhu talked about the planning process and identifying stability constraints, and really your talk really rounded it out with kind of the technical and economic piece of identifying those constraints. So thank you for that. We'd like to move to the Q&A session now. So for those of you who just joined, we're on slido.com. If you'd like to log your questions and see what questions have been asked so far, the code is ESIG21, ESIG21. I'd like to ask that all of the presenters come on video, and we'll start our session. Thanks. So with that, Ryan, would you like to pull up the Slido questions? And as Ryan's doing that, I'll start off here. And we have over 24 questions that are really deeply technical in nature, a lot of great clarifying questions. And I'd like to call on as many folks that presented, all 4 panelists as possible. So let's go down the list. The first question we have with 7 votes came early in our session. I think this was something somewhat after Julia or maybe Shawn's presentation, and it was about regarding the PLL loss of synchronism. What is the main reason for PLL loss of synchronism, and what type of wind turbines are mainly installed in ERCOT, type 3 or type 4?
Mm-hmm.
Who would like to take that one?
Yeah, I'll take that one.
Sure. Go ahead, Julia.
Yeah, so I understand these are 2 separate questions. So the first one for PLL loss of synchronism, that was mainly zeroed down on one inverter manufacturer, and they actually had voltage shift protection in the inverters that would trip an inverter at 10 degrees, I believe, vector shift and voltage angle.
Okay.
And then about turbine types, it's around 70 to 75% are type 3, and then around remaining 15% type 4, and then maybe there is a small percentage still left of type 1, type 2, older ones. And one thing I forgot to mention, I'll link up a NERC report on Odessa disturbance, so that one has much more detail about causes of trips and all of that. And then there is also NERC webinar on the event on November 5th. So I believe you can check NERC website for that.
Excellent. Thank you, Julia. And we've had quite a few questions here for Shawn on some of the clarifying points in his presentation. So there was one question, Shawn, that was voted up to the top, asking what is the criteria for selecting 36 contingencies from all possible contingencies in the stability assessment?
Yeah, can you hear me okay?
Yeah, Shawn, sure.
Okay, yeah, so that's a good question. For the PSCAD studies, actually we selected 36 contingencies. Basically, this selection, we cover all the main contingencies, N-1 contingencies within the panel and nearby panel area. On top of that, actually, we not only in the stability assessment study, we not only take the PSCAD studies, also conduct the PSSC studies as well. So by selecting those contingencies, we also get some information or the reference from the PSSC studies. Yeah, so such that we make sure all the contingencies be covered in the credible, the main contingencies can be covered in the PSCAD studies.
Great, and there's a follow-on question here, Shawn, from Ilu Liu.
Okay.
She comments, great work about the PSCAD studies that you've been doing. Have you seen any interactions between inverter-based resources in the studies that you've done?
Okay, yeah, that's another good question. Yeah, from the plots, it seems like we didn't see the issues, right? Yeah, but regarding the panel area, actually this area is keep evolving. Actually, just the recent the system change actually related with the LADEC light the system. Actually, the increase actually they add the additional path to the panel area to the main grid of the ERCOT system, such that the system strength can be improved. Yeah, so basically in our study, actually we include that path already, such that we didn't see the control interactions in the current studies. That's first one. The second one is like the second one is we only evaluate the N-1 contingency, right? But yeah, probably for the other contingency, even further, like N-2. Actually, I think that one of the other question related to this one. Yeah, probably in the other conditions, like the planning outage condition. Yeah, probably could be some issue as well with the increasing addition of the IBRs in that area, such that we need to keep study. Seems like the PSCAD study is the annual study practice in ERCOT now. We need to keep evaluating the stability condition in this area.
Great. Great. Thank you, Shawn. Appreciate that answer.
Thank you.
The next question might go back to Julia or anyone that wants to comment on it, and that is related to the detection and measurement of inertia. Is ERCOT measuring inertia online real time or looking up stated inertia values based on what units are online and running?
Yeah, so I get this question a lot. So first thing is, I think we're lucky in the way that most of the generation in our system is on transmission level. So we have great visibility of what's online, what's not. So yeah, that's exactly it. We're looking up inertia contribution of each unit that is online, and we have 4-second telemetry from every generator. I know this question is headed towards a consideration of load contribution to inertia. So we don't have visibility of that. And I know there are real-time tools that allow to estimate inertia in real time that would capture that component. But on the other hand, when we're doing studies to determine critical inertia amount or amount of reserves that we need, then we have load models in that study for with some representation of motor loads. And so when we determine what critical inertia is, it's only related to inertia provided by synchronous generators at the moment. And so when we are comparing it in real time, it's kind of apples to apples comparison. We are looking at inertia of synchronous generators, comparing it to what the critical level should be, what we found from studies that have models of motor load represented. So with that, we kind of consider at least some impact of motor loads.
Great. Yeah. Thanks, Julia, for that answer. Next couple of questions are related more to models and modeling process. So the next one we have here is about angular stability analysis. And for angular stability analysis, does ERCOT use the WEC generic models for inverter-based resources or PSSE user-defined models? Is there any preference there about how to analyze that? Great, thanks, Prabhu.
So I think there's two different things. One is that, as I mentioned in my presentation, we do require user-defined models for certain parts of the system. That doesn't mean like people don't submit generic models. So it all based on the model quality test we do. And if it is acceptable, we accept both. But majority of the cases we have gotten, like in the past, the user-defined models. And we do find that some instances it is required. Shawn can add more on the validation part of the PSCAD. But one thing I didn't mention in my presentation is that, as I said, that was the challenge when we tried to put the online tool in place, because we didn't have those models. So we made some market rule changes where we said people who are connected to ERCOT or existing resources, they have to submit both models for the planning models, which is PSSE, operations model, which is TSAT. So the effort has been going on since 2019, where people, the requirement basically says you should have exactly the same model representation. There are different softwares, but you would have the same models, but the data should be on the same format, meaning that you submit in one format, it should be able to be read by both softwares. Obviously, in this case, PSSE is the data. So that's the way we have designed it. So there's been lately a lot of these models have been developed for TSAT. We have received those. Where we started here, maybe in 2019, we didn't have enough models, but now we are catching up. As I said, we have like gone over 60%, and we would eventually get more models. So that's where we are. So different parts of the system are different, but I think for general ERCOT, its majority uses different models.
Great. Thanks for the clarification, Prabhu. I think there's a related question that's important. It's the next one that's voted up. More generally about ERCOT's experience to manage various modeling platforms, the data that goes into each platform, and how that data needs to be shared across the platforms to assess the stability risk. And I think this question was asked pretty early in the process, but I'd like to maybe expand it a little bit because it covers PSSE, PSCAD, TSAT, and we also heard Jameson talk about the production cost modeling that goes into it via stability assessment as well. So I'd like to maybe have a few of you comment from your perspectives on how do you decide how to manage that data? How do you decide to use each tool and the results of that tool feeding into other tools to assess stability constraints, maybe transfer limit constraints, maybe operational constraints? I think this is a really good question that came in and would like your opinions on it.
I can start from the operation side, maybe Shawn and Jameson, and you can add more on the planning side. It's been a while since I left planning. So operation side, as I've said, the primary challenge is like most of the times it's steady state model. We're starting to, as we talked discussion, we had TSAT a while back. It's because the DSA tool is the one which runs the TSAT, which is already integrated as part of the EMS. So we have done those, but it's more of like, existing models, or what do you call the standard models. Now we're getting a lot more of the user-defined models. That's where we have put in place a lot of those model validations recently, changes to the planning side. So typically the way we do is right now it's the planning department which manages the PSSC data, which is driving all the other applications. Basically, we're trying to match the PSSC data for operations. Same things. PSCAD is a little different. Maybe you shouldn't do that. So all the databases are right now. I mean, like at least it originates from the planning side. So the planning department basically manages the data, and we're starting to see the need in the operations side. But it's all based on our central database. It's a central station where we manage all this data.
Thanks, Prabhu. Any other comments from anyone else on this question?
Yeah, I can add a little bit onto the point. Yeah, basically for the PSSE models, actually we have the dynamic model template actually created by our department. Basically, provide the format to for the REs to customate the PSSE dynamic models, including both the user-defined model or the generic model. In that way, actually, we try to capture the model actually in a more uniform way. Also, actually, we have the model quality test requirement. That's also, whenever the model is submitted, actually, we provide the review process, to make sure the model, the performance of the model is good. Also, for the PSCAD models, we just receive it, actually start the process of a review the performance per the requirement in place, which was mentioned in my slides. With that, any other comments?
Yeah, thanks.
I can jump in real fast. So from the economics perspective, the economics model really starts with a finalized reliability case, planning model that is used for reliability assessment and is finalized, then gets handed off to economics. So for this study in particular, that same process was used, and the same start case was used for VSAT analysis. And really what kind of made this study unique was that there was almost a real-time back and forth between economics and stability analysis in terms of what limits were going to be for these options. So instead of using an estimated limit in UPlan, the tested option would be run in VSAT first, and that limit would be used in UPlan, and then ultimately fed into the more detailed dynamics models as well. So there was a couple of questions about how were these options, these three options determined, and it was really that back and forth between these economic simulations and these reliability simulations, and combining the results, and in short, trying to find the most cost-effective way to increase that transfer limit. So, from the economics perspective, if I would get a list of what looked like preferred options in VSAT or interchangeable options in VSAT, those specific limits would get run in U-Plan, and depending on what those economic results looked like, we would go back and either remove an option entirely or tweak it or keep it. So it was really this iterative process throughout the whole year. And though I only presented 3 options, we've been at this since the end of last year. So I mean, it's literally just been hundreds of options, kind of that iterative process back and forth. So that's how we've handled it so far with this study, at least.
Oh, yeah, thanks, Jameson, for that perspective. I think this practice that ERCOT is doing well, and really is a platform and a practice that many other utilities can benefit from. So thanks for sharing that. We're about at time. Julia, anything else to wrap?
Yeah, I was wondering if you could loop it back to, there was this question about how to decide when use between PSSC and PSCAD, and I actually wanted to return it back to Shawn and ask him to talk a bit about that, because this question comes up a lot, and I think it's important to answer.
Okay, I can address a little bit, on this one. At ERCOT at this point, actually for the PSCAD studies or the EMT studies, most focus on the SSR studies, as long as we identify the necessary or the risk for the project connect to the serious communication lines. Actually, ready to connect to that one. Actually, we will request the detailed EMT studies. Another one is like the weak grid area, like Panhandle or the South Texas. Actually, in this type of or the control instability related area or simulation studies, we use the PSCAD models. Other than that, we mostly focus on the PSSC or the TSAT or even the VSAT models.
Great. Thanks for that clarification. And I'm sure we'll have a lot more discussion at some of our other panels on that subject as well. But I think it's about time to wrap it up for today. So I'd like to thank all of our panelists, Julia, Shawn, Prabhu, and Jameson, for their great contributions and great discussion today. And thank you all for your great participation and great questions. It's really been fascinating discussion on a cross-section of activities going on around ERCOT. As a reminder, we'll follow up with written answers to the questions that we didn't get to during this session. And I'd also like to remind you that we'll have 2 workshop sessions being held next week on Tuesday and Thursday. We'll have a session on Tuesday on electric transportation and distribution infrastructure, chaired by Mike Hogan of the Regulatory Assistance Project. There's no charge for these sessions, and you are all welcome to attend. For further information on registration, it's provided on the ESIG website at www.esig.energy. And thank you again to all the panelists and participants. Stay safe, and we look forward to seeing you again on Tuesday. Have a great day, everyone.
Thank you.